Okay, Assalamualaikum and good afternoon to everyone. So welcome back to the second half of this semester. So how was your holiday?
Waalaikumsalam, Doktor. Uh,
Salam doktor, selamat raya.
Raya.
Salam doktor, selamat raya doktor.
Selamat Hari Raya. So, macam mana raya? Okey.
Macam lupa ada kerja.
Macam lupa dia kerja. Saya pun sama.
banyak sangat assignment.
Yes, yeah. That is the life of the student. Kalau tak ada assignment, dia akan ada benda lain pula. So it's okay. So now we are in the week number 9. So as you already aware, I already released the mark for your test. So you can refer the test mark and then decide either you want to have a subject withdrawal or not, where the deadline, if I'm not mistaken, is this week. So please decide based on your main interest. And of course, I will share your marking answer script to all of you. And then I will also share the answers scheme for both questions. So that one is for the test mark and the subject withdrawal. So today we are going to have a new lecture on the new topic. So I already shared the latest slide for today class in our WhatsApp group. Later on, I will upload it in the Google Classroom. So let's take a look on this new topic. This is the chapter number 3, where here we consider the feedback control behavior. So this is what we call it closed loop. Closed loop transfer function. So if you aware before this, we interested in developing the model where either, let's say, based on the chemical process, you will develop either based on the mass, component, or energy balance. So where the function of this balance is to obtain the transfer function. So based on the sum of the balance, in the end, you will end up with two transfer function. So that one, sometimes we call it the process transfer function, the GP, and the GD, where the GP is the process. The G stands for the transfer function. The P is for referring to the process, and the D referring to the disturbance. This one is in the case you have two transfer functions based on your derivation. If you have only one, then automatically it becomes the process. So in this case, what we have learned so far based on the obtained transfer function, we develop either the form in the first or second order. First or second order transfer function. So once we obtain the either in the form of first or second order transfer function, the next step involve the inverse Laplace, where you can directly solve the given mathematical model. So that one, if we take it overall, there is no control yet. You just assess the behavior of your process based on the first or second order. So today's topic is based on the application of control system for maintaining the process at desired level or desired set point. So this is what we are going to have today, where we want to investigate how your controller affecting or performing in the closed loop behavior. Why it is called closed loop? So we will take a look based on this given example. So let's say we have the storage tank. So the case study is the storage. Where based on this, you have two inputs, Q1 and Q2. So this is your input. And then in the outlet, you have Q3. So since in this case, we assume it is a storage tank, then of course, when we try to develop the mathematical model, you just involve the overall mass balance. Where based on the overall mass balance, you can obtain for example, the dH over dt, where the H here represent your level inside the tank. Since we have two input coming into the system, one output, then of course, depending on the value of your flow rate, the level will be changed. So when your level is going to change, then that means we need to have a control system in order to maintain the level at the desired value. So in this way, your tank will not overflow or become empty. So of course, based on the overall mass balance, when you develop the DHDT, automatically this part become your control variable. So this is the common practice based on your derivation. So based on this given example, they use the Q2 as the manipulated variable, the variable that we change or we regulate in order to make sure we obtain the desired level. So based on the table here, you have the control variable H, you have the MV, and in this case, let's say the disturbance variable is Q1. So once we obtain this table, we identify the control, the manipulator, and the disturbance, then we will be able to develop the configuration control. So this is the line is represent the configuration. Configuration control loop. So in this case, let's say you want to maintain the level, you start with the LT, where the LT represent the level transmitter. The function of level transmitter is to measure what is the current level. And then once it measures the current level, then it will send to the information to the controller. Where normally in the controller, it will compare with the set point. Compare with the set point value. The set point represent the value that we want to maintain. Let's say in this case, the level transmitter reading show that the current level is 5 meter. And the 5 meter information data will be sent to the controller, where the controller will compare with the set point value. And let's assume the set point required is 7 meter. So based on this, it shows that the current level is below the required value. So the controller see, okay, now what we want is 7, but what we have is 5. So you short by 2 meters. So when you have a shortage of this value, then that means you need to put more flow rate inside the tank. So the controller will calculate how many flow rate is needed to reach 7 meter. That is the function of the controller. So the controller will calculate the desired amount of flow rate needed to achieve the given set point. So once it's finished the calculation, then you will send the information to the control valve. So this is your control valve. So the valve will be open in order to increase the flow rate coming into the system. Then this once it's coming to the system, the level transmitter will take a reading again to check what is the current level. Let's say the next now based on the addition of flow rate from Q2, the reading now read 5.5 meter. So it will send again to the controller. Controller will calculate again, and then you go to the control valve, and then this process is repeated until the reading reach 7 meter. Once it's reached 7 meter, then the loop is stopped. It's like that. So if we take a look, this process is like starting from the H here, we go to LT, and then it will go to LC, it will go to the control valve, and then the control valve will go back to the system. So this is what we call it closed loop control, where the operation is conducted under loop, where in this loop you can see it's based on the round shape. So that's why we call it closed loop control. So in the previous lesson, before we just developed the mathematical model, that one is considered as the open loop. There is no loop over there. So the loop is open. You just have the transfer function for the level. So for this topic, we will investigate how the configuration control loop can be represented as the transfer function. So based on this, it's clear that the dH over dt here will represent your GP, the process transfer function. Now we need to obtain what is the transfer function for the level transmitter, what is the transfer function for the controller, what is the transfer function of the control valve. So this is the thing that we will be investigated in this topic. So how it is look like based on the block diagram. So basically, since we start at the H, so this is considered our GP. So this considered our process transfer function. And then here the outcome, of course, will be our H. In this case, if we take a look on the block diagram here, you have the Y. So the Y here represent the output variable, where the output variable may come in the form of the level, temperature, composition, and so on. Since we're using the liquid level control system, then your Y should be your level H. So in this case, we will have the process transfer function, then it will go straight to the level transmitter. Number 2. So the level transmitter here represent your GM, where the M is the measurement transfer function. GM. Where the function, the measurement means is referring to the transmitter. It's measured. is record the value of your level. So that's why here the output will be H. There will be additional line over here to represent the GM. And then once the transmitter measure the current level, then it will send the information to the controller from number 2 to number 3. So in this controller, like I said, it will compare with the set point. So that's why you have the comparator over here. This one is what we call it comparator. So in this case, YSP represent your set point value. So let's say, for example, in the previous case, in the previous slide, I used 7 meter as my set point, and the measured first reading is 5 meter. So this means here the error. The comparator will calculate the error. Error between the set point, I put SP minus YSP minus YM. The output of the set point minus the measurement output. So for example, in this case, 7 minus 5. So you have error of 2 meter. Positive error indicate that the current value is below than your target value. If you have error negative, it's exceeding your current set point value. It's like that. So the error here can be positive, can be negative. Positive means the value is below than required. Negative error indicate that the value exceeding your target value. It's like that. So once it's compared the value between the set point and the measurement, then the controller will take action. What is the required action that needs to be taken? So this is what we call it GC, the controller transfer function. So this represents your LC here. So once the controller obtain the error value, it will calculate the how many or what is the amount of the flow rate needed to adjust before it send information to the control valve. The control valve here is this one is your GV, valve transfer function. The GV stand for the V is stand for the valve. G is the transfer function. So the function of the valve is of course either to increase the flow rate or to decrease the flow rate. How much it will be increased, it will depends on the value obtained from the controller. So this is your GV. So after the controller, it will send to the number 4, the GV. And then the GV, once it's regulate the flow rate coming into the system, it will go back to your process transfer function. So this is what we call it, the closed loop transfer function, where it will contain the process transfer function, valve transfer function, controller transfer function, measurement transfer function. And in some cases, if you have the disturbance, then it will be included. It will depends. This is normally obtained from your derivation. When you derive, if you get one transfer function, then you only have the GP. In some cases, you may get 2 transfer functions. That means one of them will be processed, one of them will be your disturbance. How to differentiate? It will be based on the selection of control variable and manipulated variable. Normally, for the GP, the transfer function should be the control variable over manipulated variable. The GD, control variable, disturbance variable. It's like that. So this is the way how to differentiate your process or disturbance transfer function. So here you can see based on the block diagram, you have the loop. So this is the loop where it will be keep repeating again. It will be iteratively repeated. So this is what we call it closed loop control system. So any questions so far? All right, if there is no further question, then we continue. So based on this block diagram, this is what we call it a standard. The standard closed loop block diagram, where you have one output, the Y here, your output, and then you have two input based on the block diagram, where the input coming from the set point and the disturbance. So now based on this, we want to take a look on how we can obtain the closed loop transfer function for standard block diagram. So let's take a look on the notation. In this case, if we take a look, you have this one and this one. So what is mean by that one is normally that one is the summation. If you have the plus plus, that means the output C and the input A and B. So it will be equivalent to the C equal to A plus B. Because you have the plus plus over here. If you have plus negative, that means the output will be obtained by substituting A into B. So this is what we call it comparator. And this one is the summer, or sometimes we call it summation. So this is the two commonly used notation, either the comparator plus minus or plus plus. You don't have the negative minus minus or negative negative. Normally you only have plus plus or plus minus only. And then here we have the block diagram. So normally here the block diagram G. G is your transfer function. If we take a look on the definition of transfer function, Gs equal to output over input. So this is the definition of the transfer function. When you developing the transfer function from the mathematical model, you will assign, you will identify which variable is the output, which variable will become your input. So the transfer function will be developed based on the output variable over input variable. So for this case, the output for your block diagram here is Y. So this is your output and the X is your input. So meaning that you will have the YS over XS. So if we try to rearrange it, it becomes the YS equal to GXS. So this is how we can alter or we can develop the relationship between input and output from the block diagram. So if we have it in the series like this, you have the G1 and then it's connected to another block diagram, which is the G2. So we develop from the definition of transfer function where here the GE1 S equal to X2 over X1. And the G2 S equal to Y over X2. So from this case, we know that the G1 equal to X2 over S1. Then X2 equal to G1 X1. And then for the second part, for the second transfer function, G2 equal to Y over X2. So we can further rearrange Y equal to G2 multiply with the X2. So we have like this. Then this one can be further rearranged where you have the x2. The first transfer function, x2 is your output. Now it becomes your input. So you can substitute the value inside the y relationship where now y equal to g2, g1, x1. Where now we can see this is your y, this is your x1. So y is your output and then x1 is your input. And then inside the relationship, you have two transfer functions, G2 and G1. So this equivalent to the given block diagram. Like this. So this is your Y. So from two block diagram in series, we can combine it into single block diagram based on the relationship output over input. So this indicate that we can further develop the overall closed loop transfer function for this standard block diagram. So let's take a look. In this case, here we use the standard block diagram where we have Y as our output, D is our input, YSP is our input, second input. And in this case, I put the A, B, C, D, E, G, F, and the H. Why I put this one? To establish the relationship between output and input for every transfer function. So once I put the label, then I can develop the relationship between input and output. So that's why I put the A, B, C, D until H. Of course, you can use another symbol if you want. This is just for illustration purpose only. So by having the labeling, then I can set up the relationship between input and output. I start from the left to the right. So here I start with the KM. So where the KM here, you have the input YSP and the A. So this means KM equal to A over YSP. Where A is my output and YSP is my input. For the GC is B and C. So you have the GC equal to C plus C over B. C is your output and the B is your input. And then the GV. The GV relate the C as your input and E is your output. Then you have the GV equal to E over C. And for the GP, I have E and F as my input output. So when I try to develop it, it becomes GF equal to F over E. For the GM, here, this one, the line is splitting. You have two split lines, this one and this one. So when it's splitting, it still carry the same symbol. So this means the second line represent the Y. So for this part, the Y is your input and the H will become your output. So that resulting into GM equal to H over Y. And lastly, the GD. So the GD, you have the G and the capital D. So that's contribute to the GD equal to G over D. So this is the transfer function relationship between input and the output according to the label in the block diagram. So we finish the relationship for each transfer function, then we can further develop for comparator and the summiter, this one. So where here, the comparator, you have include we include the A as the plus and then the H is the minus. So the outcome will be B. So this means B equal to A minus H. So where this one positive and negative. So A will be positive, the H will be negative. So you get B equal to A minus H. And the other summator here, the summation, you have F plus G. So the F here is positive, the G is also positive. So you get Y equal to F plus G. So this is the relationship. So why we need to develop this relationship is because we want to obtain the overall closed loop transfer function. So based on this different block diagram, we want to have a connection from the bigger output, where now I want to, this is my boundary right now, the biggest boundary. So meaning that in the end, my transfer function should be like this. This is my Y, this is supposed to be the D, and this is supposed the YSP. So the problem is, what is the transfer function inside? So that's why here I want to obtain that. I put the labeling and I establish the transfer function relationship. So from here, then we can start doing we can replace or we can expand our equation. How to start? Normally we start with the output, because here we have Y as our output. So we start with the Y. So the Y is this equation. Y equal to F plus G. So in this case, we know that Y equal to F plus G. Now we want to know how we can substitute the F and the G. The F coming from the process transfer function, where the GP equal to F over E. So in this case, the F equal to GPE. And then the G here is based on the disturbance transfer function, where you have the GD equal to G over D. So when we try to rearrange the equation, you get the G equal to GD multiplied by D. So this F and G then will be substituted into the Y equal to F plus G, which contributing to the following transfer function. So you have the GPE, you have the GDD, you put back into the original equation, then you can get Y equal to E multiply GP plus capital letter of D multiply with the GD, the disturbance transfer function. So from here, we next establish what is our E. So here the E is based on the valve transfer function. So you have the GV equal to E over C. So here the E become GVC. So we substitute back into the equation. This contributing to the C GP GV plus D multiplied by GD. So here do we need to change the D? So here the D, you don't have any relationship, because this is the location of D. Is your input. There is no relationship over there, because it's the starting point of your input. Then that means you don't need to replace it. That's why here you stick with the D multiplied by GD. It's already finished this term. So based on this, we take a look again. Y equal to C multiplied by GP and GV plus D multiplied with the GD. Where now we want to find the C. C is based on the controller. GC equal to C over B. So for this part, we know that C equal to GC multiplied by B. So we substitute again into C. This resulting into the following transfer function, following equation. where now you have the y equal to b multiplied by gp multiplied by gc plus d multiplied by gd. So we complete that part. So now still we have the unknown relationship with the b. So the b coming from the following equation, a minus h. So this is coming from the comparator, where a carry the positive signal, the h carry the negative signal. So when we substitute a minus h into b, you get the following equation. So what is next? So now we want to make sure the relation a and h to be substituted. So this coming from the Km bar. So in this case, you have the Km bar here. This one, normally what we call it set point transmitter. Km bar set point transmitter. Since you have the K, that means gain. Gain of set point transmitter. So that is the Km bar. And then the H coming from the Gm equal to H over Y. So this indicate that both can be substituted into the equation, which resulting into the following transfer function. So based on this, you can see that the y equal to in bracket Km bar YSP minus Gm Y. Close the bracket, you have the Gp multiplied with the Gv multiplied with the Gc plus D multiplied with the Gd. So all of the variable has been substituted in the following equation. So what is next? What is next? Then we take a look. Also, you have the y on the left hand side, and then on the right hand side, you have the y. Of course, this means you can do the factorization. So in order to do so, you need to expand the equation first. So this contributing to the y equal to Km Gp Gv Gc Ysp minus Gp Gv Gc Gm Y plus dGd. So you have y on the left and the right hand side, you put it on the left hand side since it is output variable. So you have y over here, then you can do the factorization. So y in bracket 1 plus Gp Gv Gc Gm equal to Km bar Gp Gv Gc Ysp plus D multiplied with the Gd. So lastly, we can obtain the relationship where now you have the y, Ysp and the D, where y is your output. So this is your output. Ysp is your input number 1, and the D is your input 2. So this is what we call it overall closed loop transfer function. How to use it? We will discuss it later. This one is just how we develop the overall equation for block diagram. Any question?
Doctor, may I ask about for the diagram how we can identify the symbol of the plus minus? Because still confusing about it.
Okay, sure. Thank you. All right. In this case, this one, okay, I refer to this one. All right. So this is what we call it standard closed loop block diagram. That means the arrangement is fixed. How you get this arrangement is based on the closed loop configuration, where you start with the LT, LC, and the valve. So this is the standard arrangement. It's not going to change. So that's why from there, from the configuration, you obtain the closed loop block diagram. So normally, in this case, the plus minuses, normally we call it as an error calculation between the set point minus the measurement value before it send the information to the controller transfer function. So that means it is fixed, plus and minus. The minus may come from the output from GM. And the positive here coming from your set point. So the location is fixed. So whatever the question you have, the situation you have, the case study, we implement the same location of the block diagram, where this is the location of the plus and the minus. The same goes with the comparator here, the plus and the plus. This one normally is obtained from the transfer function. Let me give you some idea how you get the GP and the GD to get a better understanding. Okay, let's say here we have the energy balance. For example, energy balance. So let's say you have the rho V Cp dt over dt. You have F Ti minus T plus Q. All right. This is just for the sake of example. So based on this, let's say here we assume the flow rate is constant, the rho VCP, the volume is constant, the density and the heat capacity, of course, are constant. So this means based on the derivation, T prime, Ti prime, T prime, and the Q prime, where the Ti is the inlet temperature, the T is the outlet temperature, and the Q is the heat addition to the system. So based on this, according to the previous procedure, you need to do the Laplace. So you will do the Laplace rho VCPS T prime S equal to F Ti prime S minus T prime S plus Q prime S. So we will have the T prime over here on the left hand side and the T prime on the right hand side. So you can put it together on the left hand side. You get like this. Plus F T prime S equal to F Ti prime S plus Q prime S. So based on the factorization, rho VCPS plus F equal to F Ti prime S plus Q prime S. So you have the T prime S equal to F rho VCPS plus F, for example, Ti prime S plus Q rho VCPS plus F Q prime. All right. So this is just the example just to give you the idea how the GP and GD can be obtained. So based on the following transfer function, based on the following mathematical model, you have one output. So the T prime is your output. The Ti prime, the Q prime represent your input. So this is your output. Input 1, input 2. So what is mean when you have the single output but two inputs? This indicate that you have two transfer function. Where you may get T prime S over Ti prime S. So this is the first transfer function. And then the second transfer function will be the T prime S over Q prime S. So since you have two transfer function, that means either one will be your GP and another one will be your GD. The question is which one? How to know? This we go back to the basic. Normally, when we want to set up for the control system, we need to select what is our CV, what is our NV, and what is our DV. So based on the given example, the control variable is the T, temperature. And what is our manipulated? Any answer?
Manipulator Q.
Why?
The heater will be affect the most of the temperature.
Yes, correct. So that means the MV will be our Q and the disturbance automatically is your Ti. So here the Q will give the more influence or more affecting to the temperature. That's why we select the Q as our manipulated. So when we have like this, that means our GP definition is CV over MV. The GD definition is CV over DV. So here the control variable will be our T divided by manipulated Q. And then the control variable for the GD still the temperature and the disturbance will be the Ti. It's like that. So this indicate that T prime over Ti prime here is our GP, our GD. And this one is our GP. So that's how we can develop the GP and the GD. In this case, the question is why it be positive and positive. So we take a look on this symbol. So here, this one belong to the following transfer function. So this is the transfer function for the T over Ti prime. And this is the transfer function for the Q, T over Q. You can see that this represent the positive. Positive, this one is also positive. Because you cannot have the negative flow rate, you cannot have negative density, volume, or the seat capacity. So you will get the positive value. So when you have the positive, so this is positive. This is also the positive. So this contribute to the positive GD, positive GP. So if we try to relate it with our transfer function, it becomes like this. We know that the GP is T prime S over Q prime S. And then the GD equal to T prime S over Ti prime S. So where this one, we can further rearrange it. T prime S equal to GP Q prime S. And then this one, T prime S, GD, Ti prime S. Or if we take a look on this one, this is your final equation. T prime equal to F over rho VCPS plus F. So this is your GD. And this is your GP. So if we try to reconnect it, it becomes T prime S equal to GD Ti prime S plus GP. Q prime S. So since both is plus, that means if we try to represent it, the block diagram is like this. Positive, positive. This one is your T. So this is your Ti prime S, and this one is your Q prime S. So this is your GD. This is your GP. So that's how the positive coming from. So normally, when we try to derive it, as I shown it here, of course, both are positive. Because the Ti and the Q is identified as your input. So that means when you have the input, of course, it becomes the positive. So based on this explanation, that's contribute to why this part is always positive. You have the positive, and this one is positive, negative. It's like that. So in this case, based on the given example, normally this part, the one that I show here, how to get the GP and the GD from the transfer function. So this means the GP and the GD, if it's not given, both can be derived from mathematical model. So I think you can imagine right now, in the final exam question, if the GP and the GD is not given, then you have to go the earlier step, which is to derive the mathematical model. So it's such a long way. So we already have the GP and the GD, the KM bar, the GC, GB, and GM. I will explain it later how to obtain it. So for time being, if we have the configuration like this, where you have the LT, the transmitter, the controller, and the valve, then this is your standard block diagram. This is what we call it standard. It's not going to change. And from this standard block diagram, this is your transfer function. It's not going to change. So you just adopt it. You just use it directly if you have this kind of the block diagram. How to know? First, if the question gives you the standard block diagram, so you just use it. Or if they give you in the form of configuration control loop, you check. You need to have this item, the transmitter, the controller, and the valve. So when you have these three items, automatically this is your standard block diagram. It's not going to change. So from this standard block diagram, you will have this one. This is what we call it overall. Overall closed loop transfer function. And from the overall, we can split it for the Y over YSP or Y over D. So what is the difference between Y over YSP and Y over D? Is sometimes when you have Y over YSP, it's called as the set point changes. So because this one is based on the set point. So the output determined based on the set point changes, the YSP cannot be 0. So you neglect the D equal to 0. So in other way, from this overall closed loop transfer function, when the problem is based on the set point changes, you neglect the GD. It's like that. So you obtain the Y over YSP. So this is known as the servo problem, or sometimes we call it the set point tracking. You change the set point, you see how the controller is behaved. So this is the mathematical representation to measure how your controller is behaved. And another one, this one is not set point changes. Okay, this one is changed to disturbance changes. Disturbance changes. So based on the disturbance changes here, the D cannot be 0, but YSP will become 0. So for the disturbance changes, from the overall, you neglect the YSP. So you have the Y equal to GD over 1 plus GP, GV, GC, GM multiplied with the disturbance variable. So for the disturbance changes, your set point change is neglected. And this is known as the regulator problem. The difference is the set point changes, you change the set point. For example, for the case of the level, initially you set 7 meter as your set point. After 5 hours, you want to change to 8 meter. So this is what we call it set point changes. For the disturbance changes, we see how your disturbance affecting your problem. Of course, in the control system, we have the control variable manipulated disturbance. The good controller should be able to maintain the process at the desired set point, and also to able to reject any kind of disturbance. So how to measure it? We based on this mathematical model. So we have to separate either the set point changes or disturbance changes. If we want to consider both, then it becomes the overall closed loop transfer function, where here you have consider the set point and the disturbance changes. The SP is there, the disturbance also there. So this is the overall. So sometimes in the final exam, we will specifically mention either the process for the problem, consider the overall or the set point changes or the disturbance changes. If the problem referring to the disturbance changes, you just use the following equation. You just take it directly. You don't need to derive it. You just take the standard form, you just replace the transfer function inside the equation. It's like that. So any questions so far?
Doctor.
Yeah.
So usually the disturbance is something that can be calculated, right? So,
Yes.
so that the can be changed.
Yeah.
So
For example, in the if we refer to this one, like this one, okay. So here the disturbance is the Q1. So this means the value of Q1 is coming from here. So normally the Q1 is the first for it. So you have the value. Maybe first you put 1 kilogram per hour, and after 5 hours you change to 2 kilogram per hour, and you can observe what happened to your set point later on. Okay.
so usually like falling or pressure difference in the part cannot be considered as disturbance, right?
No. The one usually is fixed. It's a constant value. So that one is not considered as a disturbance.
Alright, Doctor.
Alright. Okay. So we finished the standard closed loop transfer function. And of course, sometimes you may ask, why in some cases you have the IP, the transducer? So you will encounter the configuration loop like this. So here is a little bit different compared to the standard one. So why it is different? So in this case, you can see this is the case study. For A is the analyzer. A for analyzer, that means is for the composition control. So meaning that the Y here is for the composition. The composition in this case will be your X, the X composition. So in this case, we can see that first you have the AT. So A is the analyzer, T is your transmitter. And then you have the AC, C the same, analyzer controller. After the transmitter, you get the controller. And then here the problem, you have the IP. So what is the IP actually? IP is sometimes we call it as a transducer. Transducer. What is the function of transducer? If you take a look, before the line coming to the empty, the IP, you have the arrow with the dash line. And then after the IP, you have the arrow with this line. So if you may recall for the PNID diagram, the dash line represents the electrical line. And this line is called pneumatic line. And if you have the solid line, then this is what we call it piping line. So normally the transmitter, the controller is an electrical device, electronic device. So, and then the valve is normally operated based on the Eastern. How you are going to open the valve? Either you turn on, you turn off. How many you turn? Sometimes it's based on the quarter, half, 3/4, it's like that. So in this case, you need the tools to convert the signal. Since the controller is electrical device, is based on the electrical line. Then the transducer will switch the information from electrical data into the flow rate. So this is what we call it pneumatic line. The function of transducer normally is to change the signal from the electrical into pneumatic data. So this is another form of configuration control loop. So since this is, you have one additional symbol located in the configuration, that means your block diagram will be changed. So that's why in this case, you have a little bit different transfer function, where now still you have the GP. The GP is the similar, the GD is location is similar. You have the GM, KM bar. And then after the KM bar, the set point, you have the AC, the controller, you have the GC. And since the IP is located between the controller and the valve, then that means you need to include the block diagram. So this is your additional block diagram involving the IP transducer. And after the IP, it go to the valve. So this one is tally with the block diagram is tally with the location of your IP in the configuration control loop. So what happened if we include additional block diagram like this? Then that means your overall closed loop transfer function will be changed. So how it look like? When we include the GIP, then you can see you have the GIP inside. So this is how the overall closed loop transfer function for this block diagram can be obtained. So here again, we can do the derivation to prove it. Since in this case, I already show you the standard block diagram derivation. So here I don't need to show it anymore. So I just show the final version. So when you have the GIP inside the block diagram, so this is your closed loop transfer function looks like. Where now for the Y over YSP, you have the GIP on the numerator and denominator. But for YD, only at the numerator. You don't have GIP inside the numerator. So this is how it looks like. So this means for this case, normally you have two types of block diagram. Either the standard one or sometimes with the IP like this. If the configuration, you have the IP here, then this means you need to use the following equation. If there is no IP, then you use the standard block diagram. This, the thing you need to be very clear. How to know? Read carefully the question. Check, is it any information relating to the IP or not? There will be included this data on that. If you don't have any IP, you use the standard one. So this information, I think, is not available in your textbook. So please understand carefully. Of course, later on, I will provide additional tutorial for you to enhance your understanding. So for time being, there are two block diagrams, the standard one without the IP, or the alternative one with the IP. So inclusion of IP will contributing to the final overall closed loop transfer function, as you can see in this slide. Any question? Okay, if there is no question, then we take a look. Form of transfer function. Again, if you take a look, some of the information, this one can be found in your textbook. Here, if we refer to the third edition, this one is third edition textbook, is on the chapter 10. Page 176. Starting from the page 176 to 180 something. So this is if you want to refer to the textbook. However, some information is not available in your textbook. For example, the inclusion of the IP. It does not describe in your textbook either for the third or the fourth edition. So I think that's why this one you can see some new information to complement the shortage of the lack of information in the textbook. The same goes with this slide. It's not explained directly in the textbook. I put additional notes for this part. So based on the transfer function here, you already familiar with the GP and the GD. This one has been familiar. So if we, for the GP and the GD, either you can derive from overall mass, component, or energy balance. If it's not given to you. For a final exam, normally we didn't give it to you. You need to derive it by yourself. Or sometimes maybe we are too kind, we give you the information either in the first order plus time delay, second order, or the first order plus time delay. So this is the standard form for either the GP and the GD. Again, I repeat, the GP and GD, if it's not given in the question, then you need to derive it. And if it's given, then normally in the form of the first or second order, with or without the time delay. So this is for the GP and the GD. And how about the KM? So the KM bar here is stand for the set point transmitter. So since you have the K here, that means it refers to the gain. What it means when you have only gain? You don't have any first order. For example, the first order, you have K over tau S plus 1, where this one is your gain. And the tau is your time constant. So whenever for the set point transmitter is the gain, that means you don't have the tau. So you only have the value of the K. It's like that. If I put G, it can be in the form of the gain or the first order. It's like that. So here the gain can be calculated from the given formula. Delta output over delta input. Or sometimes we give you the number. The gain for the set point transmitter is 1. It's like that. Or sometimes we give the set point transmitter value other than 1, 2, 3, any real number. It can be positive, it can be negative for this one. Because this one represents the set point transmitter. So the set point sometimes can be increased, can be decreased. If increase is positive, if decrease, then maybe it becomes negative value. So both are acceptable. For the set point transmitter, you don't have any time constant. Unlike the set point transmitter, you have the GV, the GM, the GIP, the valve transfer function, measurement transfer function, or the transducer transfer function. There are 3 forms for this transfer function. Either the K, the gain only. That means the K. So if it only the gain, then delta output over delta input. That means, for example, here when you have the gain only, no time constant. The time constant equal to 0. So you get the gain in the form of the GV. On GV equal to K. And sometimes this form may be in the form of the first order, like this, or second order. It depends on what kind of the transfer function we give it to you. Normally, this is the standard, either gain only, or first order, or second order. So unlike the GP and GD, you need to derive. But the GV, GM, GIP, the information is directly given to you. So you don't need to worry about that. Alright, this is further example. just to have a clear idea on how the transfer function is given. So this example is based on the liquid level control system. Here you have the overall mass balance where you have the A dH dt equal to Q1, Q2 minus Q3. So since the Q3 here, you have the valve. So this means I change the Q3 equal to H over R, where the R is the resistance. So based on this, I put in the form of derivation, you have the A dH prime dt equal to Q1 prime plus Q2 prime minus H prime over R. And then I did the Laplace transform. So I obtained it as H prime equal to Q1 prime plus Q2 prime minus H prime over R. Where here I can do the factorization. I put it on the left hand side, I get H prime equal to R over AR S plus 1 Q1 prime S and plus R AR S plus 1 Q2 S. So like the one I showed you before, this one you have two transfer function. The H1 over Q2 prime and then H1 Q1 prime. So since in this configuration, it shows that the Q2 here has the valve. So when the Q2, the line has the valve, that means this is your manipulated variable. So the H over Q2 is your GP. And the Q1 here, H1 over Q1 become your disturbance transfer function. So once you obtain the R, the resistance value, the cross-sectional value, then you can substitute into the equation, you get the first order. So it's like that, how to obtain the GP and the GD, and how to differentiate. If you have two transfer function, which one is the GP and GD is based on the which one will be your manipulated and which variable will be used as your disturbance. Alright, that one is for the GP and the GD. Now, we take a look on this example. The input range of temperature transmitter. Temperature transmitter is 50 to 150 degrees C. And the output is 20 milliampere. So this one, if we take a look on the first sentence, the input range of temperature transmitter. So here the term is transmitter. So this referring to the GM. And then the second sentence, the information give it to you, the steady state gain control valve is 5. And lastly, the sentence, the second sentence, the steady state gain of the control valve. So this referring to your GV. And last sentence indicate that transmitter and control valve dynamic are negligible. What is mean by that? So we take a look. So here we know that the input range of temperature transmitter is 50 degrees C to 150 degrees C, and the output is 4 to 20 milliampere. So we assume the GM in the form of the first order. So in this case, the problem here, the gain is given in the range. Input 50 to 150 degrees C, output from 4 to 20 milliampere. So this means the gain for the measurement need to be calculated based on the formula data output over data input. So based on this, we take the value of the output, which is 4 to 20. So this means the delta output will be 20 minus 4. So we take it directly from here. So since this is your output, and the input is 50 to 150 degrees C. So this is your input. It's okay if you put like this, 4 minus 20, 50 minus 150. Also, you have the same answer later on. No problem. As long as you use the given range as stated in the question. So based on this, your gain is 0.16 based on the calculation of data output over data input. And then in this case, we get the Km value. So the Km value, we obtain it. How about the tau M? All right. So this can be referred to the last sentence. The transmitter and control valve dynamic are negligible. So normally if this term is used, that means it's referring to your tau, time constant. Dynamics are negligible, referring to the tau M and equal tau V equal to 0. Because it's negligible. Why is called dynamic? It's like this. If we put the value, okay, for example, Km equal to 0.16, your graph should be like this. So this is 0.16. If your Gm equal to Km equal to 0.16, when you don't have any negligible, you only have the gain, then the graph will be this flat line of 0.16. If you have the first order, Gm equal to 0.16 over 2s plus 1. Now you have tau equal to 2. So this contributing to the following line. It will start from 0 and then it will reach 0.16. It's like this. So this is the first order for the given transfer function. So that's why here it's called dynamic are negligible. That means when the dynamic is negligible, the graph is static. So that's why in this case, when you have the dynamic are negligible, the tau time constant equal to 0. It's like that. So for this case, the Gm equal to Km equal to 0.16. That means you have only gain for your transmitter. And for the second, the control valve, the GV equal to KV tau Vs plus 1. For this part, the gain given directly to you. You don't need to calculate it, you just use it because it gives the steady state gain of 5. Then that's why the KV equal to 5. Since the control valve dynamic are negligible, of course, you have tau V equal to 0. This contribute to the GV equal to KV equal to 5. So this is how you extract the information for valve transfer function or the transmitter transfer function. So this example just to give you idea how the GP, the GD, the GV is given to you. So this one of the example of that to demonstrate that.
Sir,
Yeah.
yang tekan yang formula yang saya tulis kat belah kanan GM equal to 0.16 bahagi tau MS tu saya tulis apa?
So MS.
Yang
Alright. Yeah, alright. So here I put this one GM equal to KM tau MS plus 1. Alright. So this one, if you refer GS, transfer function equal to K over tau S plus 1. So this is the general transfer function. So here, if you compare with the GM, why I put the M? What is the difference? So this M referring to the measurement. The tau M here, time constant for measurement. Only the labeling is different. but still in the first order. Only I want here to differentiate the symbol. Because in this case, you can see sometimes the GM in the first order. You can refer to this one and this one. Both are in the first order. So I put the subscript M and the V. M stands for the measurement. And the V here stands for the valve. So in this way, you will not get confused like that. So for this part, for example, the GM equal to KM over tau MS plus 1. The KM can be calculated equal to the data output over data input. So based on this, you get 0.16. So Km equal to 0.16. How about the tau M? The tau M here referring to the measurement time constant. So for this part, since the transmitter are negligible, dynamics are negligible, then tau M equal to 0. That's why in the end, you get Gm equal to Km equal to 0.16. It's like that. Just one more thing. Sometimes transmitter and measurement is the same thing. Or sometimes we use a sensor. It's the same thing. Transmitter, measurement, and sensor is referring to the GM. So this is referring to the GM. It's like that. Okay, Kev.
Okey tu sir, yang tu je yang dekat yang belah kanan yang ada graf tu kan, yang tarik ke atas tu kan, GM equal to 0.16 over 2S ke Dr. Buat?
Yang ni for the example. I
Okay,
want to
faham.
show why dynamic are negligible. What is mean by that?
Okay, Doktor, faham.
Any other question? So here, based on these two slides, this is how to get the GP, the GD, and this one is the GM and the GV. So lastly is the controller transfer function. So the controller transfer function is different. So this means we have the form of it. So here the GC, C stands for the controller. So here we have a different type of controller that can be used to maintain the process at the desired set point. And this is the standard transfer function. That means you just use it. So there are 4 types. The first one is the simple one, what we call it proportional controller. Proportional controller where you have the GC equal to KC. The KC here represent the controller gain. So whatever when you encounter with the K, that means it's referring to the gain. The same goes with the measurement here. You have Km. So K is the gain. M for the measurement. For this part, you have Kc. K is the gain. C for the controller. So for proportional controller, you only have one controller gain, one parameter, which is controller gain. And then second type is what we call it proportional integral, PI controller. So this is the PI controller. So in this PI controller, there are additional terms included. So you have the Kc, you have the tau I. The Kc is the controller gain and the tau I is the integral. I stands for the integral, integration. And the tau, of course, the time constant. So in this case, you have two parameters, Kc and the tau I. The S over there is the Laplace. And the third case is you have the PID, proportional integral derivative, PID controller. So this one, you can see there are three parameters, Kc, tau I, tau D. Kc is your controller gain, tau I, integral time constant, and lastly, the tau D. D stands for the derivative. Derivative D, the tau time constant. So that is the third one. The PID, we call it, the short form. The P controller proportional. PI, proportional integral. PID, proportional integral derivative. And lastly, you have the proportional derivative, no integral. So you have the Kc and tau D only. So this is the standard controller transfer function. If the question asks you to use PI controller, then you just use directly the given transfer function. You don't need to derive it. You don't need to calculate it. You just use the following form. The value of the Kc, tau I, tau D will be given to you. Like that. So I can see this one is getting complicated. That's why this is called PCD. So you already know that based on the closed loop transfer function here, we have the following term: Gm, Gp, Gv, Gip, Gc. So now we have the introduction of each term. So what we can do of it, when we have the term, we insert into the equation, what we can achieve from the following transfer function. All right, this is the next story. So this is the flowchart, the workflow on how we can use all of the transfer function. In this case, we want to evaluate the closed loop control. We put the controller, so we want to see, is it our controller able to maintain or not? In the real situation, in the chemical industry, we can see it online. We see the graph, okay or not. So since this one, we don't have the online, we need to go to the basic from the mathematical equation. So here, this is the starting point where we start with the transfer function identification. We identify which transfer function involved for our problem. We find it, determine, we obtain the GP. What is our GV? What kind of controller? Do we have the transducer? Do we have the measurement and the set point transmitter? We collect the information. Once we obtain the information, then we employ the closed loop transfer function. Based on the question, it will state you need to construct the overall or the set point or the disturbance. Normally only one, don't worry. We don't ask you to develop all of it. We just state either the set point or disturbance, like that. So if the set point changes, then that means you need to use the set point changes equation like this. So you will just use this one. If the state the disturbance changes, it will give you this one. So you just use directly based on the given statement. So once we know what is the changes, either this set point and disturbance, we do the offset calculation. So what is mean by offset calculation? So for example, So this is our target set point. For example, if we refer to the level, I want the level maintained at 7 meter. And then based on the controller, I calculate it. Oh, now my measurement is around 5 meter. So this is what my controller can achieve. So this means the offset here, 7 minus 5, so equal to 2 meter. So the offset is 2. That means you shortage by 2 meter. So that is what is meant by offset. So here the objective, we want to evaluate the controller performance. We put the controller. The controller function is to maintain the process at set point value. To maintain means to reach the value, to reach the set point value. So here we can assess by mathematical equation. We calculate it. Do we get the offset value or not? So that is what is called the offset calculation. And lastly is the performance evaluation. From this graph, we take a look. You can see here, from this graph, 1 here represent the set point. So in this case, you have the controller, different value of the controller. Kc is the controller gain. Kc equal to 1, Kc equal to 2, Kc equal to 5. You can see when you put the Kc equal to 1, this is the Kc equal to 1. The performance is well below the set point. So can you further improve it? You put another value of Kc, you check. So when you put Kc equal to 2, you can see the response is slightly better than Kc equal to 1. It's getting closer with the set point. So you increase to the 5. So when you see this line, the solid line is getting closer to your set point, which is indicate the improvement. So this is what we want to observe by doing the closed loop control system. All right, and lastly is the offset calculation. Here the offset calculation definition is the difference between your target value and the current measured value. So you have the offset equal to y prime sp infinity minus y prime infinity. Or sometimes this one is based on the deviation. And in some cases, you don't have no deviation, no prime inside the equation. So this can be obtained from your equation. So the main problem here is in bracket you have the infinity. This means we just obtain the offset value at final time. So of course we can obtain it in the different time, but normally for this part, we just concentrate on the value at the final time, which is normally it is considered as the infinity. So offset is calculated at t equal to infinity. So here, this offset calculation is applicable either for set point or disturbance changes. So this means you can do it both, no problem. So the offset is just to indicate the deviation between the target and the measured value. So the YSP normally is based on the magnitude. So this is like the step input. When you do the first order, you have the step input. The same goes with the YSP here, where you have the M. So if we recall the set point changes, you have this equation, right? Y prime S over Y prime SPS equal to Km GP GVGC over 1 plus GP GVGC GM. So the YSP here is based on the step input. So you have the magnitude of change, you Laplace it, you get M over S. So we substitute the y prime SPS into the equation here. You get this problem. We substitute y prime SPS with the m over s. So in this case, we have the y prime s. So for the offset here, the YSP infinity minus the Y prime infinity. Y prime SP infinity can be represented by your offset. So Y prime infinity, how to get it? You need to use the final value theorem. So the final value theorem indicate that when the time equal to infinity, S becomes 0. So this is the criteria for final value theorem. Is specifically to obtain the output at time equal to infinity. This is the function of final value theorem, to determine the value of your output at time equal to infinity. So according to the final value theorem, when the time equal infinity, S equal to 0. So what happened when you have the S equal to 0? So this is your equation. This is the formula. Formula for the final value theorem, where limit S equal to 0, Y prime infinity equal to S multiplied with the Y prime S. So Y prime S is equal to Km GP GV GC over 1 plus GP GV GC GM multiplied with the magnitude over S. So for this case, you can see the S normally will be cancelled. So if you encounter with the other S later on, it will be equivalent to the S equal to 0. So this is the final value theorem calculation. And lastly, the performance evaluation, we want to sketch the graph, the diagram, how far your performance is deviate from your set point value. So this can be done later on. All right. So this is the tutorial that I think I would like you to refer it to see how the workflow can be implemented. So since now we almost reached the end of our class, so please refer to this tutorial to enhance your understanding. In this case, I think I put step-by-step procedure. I put the GP, the GD, and then I show the calculation. And this is a step-by-step how to include the transfer function inside the overall closed loop transfer function for set point changes, and how the offset calculation can be done. So this, I think you can refer it by yourself because this is the step-by-step procedure. So this is the thing about the closed loop behavior. So I give you the time to study it again, to have a revision on it, because I think this is the crucial part. This normally represent one question in the final exam. So take your time to study it again. In case you don't understand it, you may ask directly with me. And in addition to that, if we refer to the WhatsApp group, I also include another tutorial. So if you refer to the slide, to the attached document, so this is another tutorial for you. This is combination, I think. So okay, this one is already included. You can refer it to this one as well, no problem. So study this case, and then I will provide another tutorial for your practice. Any last question before we end our class? Okay, I think that's it for today. Again, thank you for your information. I give you time to study the notes, the tutorial, and then feel free to ask me if you have anything. So with that, thank you very much again for your participation today. Have a nice afternoon. Have a good lunch to all of you. Thank you. Class is dismissed.
Thank you, sir.
Thank you, Ada.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.